Hi, my name is Aida. I'm a PhD student at the University of Washington working with Professor Hajishirzi. We want to welcome you to the virtual presentation of our work on procedural reading comprehension and also thank our co-authors, Antoine, Bhavana, and Yejin. We refer to process as sequence of events describing changes in the properties of the main elements that are participating in the process. Procedural text describing the process can be found in various domains, for example, the cooking recipe or the scientific process or a mathematical problem can all be seen as procedural text. To give an example, here is the procedural text describing a scientific process. We want to illustrate how we can map from text to find the location attributes of the entities, fuel, and mechanical energy throughout the process. By going through the first sentence, the engine must be powered by gas or some fuel source. The reader can easily infer that the location of the fuel is now engine. But looking at the second sentence, the fuel source will power an alternator poses new challenges as we see that there is a change in mechanical energy, but the entity term is not explicitly mentioned, and the reader should refer to the word power to infer that there is a new type of energy that is getting created. We are also interested in looking at the transitions that are happening from one time point to another in the attribute values, and we refer to them as transitions. The problem of procedural reading comprehension is a problem defined as given the input of procedural text and the list of entities, we want to track the attribute and transition values of those entities throughout the process at every time point. By doing so, we can answer high-level questions, for example, what is happening to the fuel? And by looking at the table, we can easily infer that it's getting converted to mechanical energy through an alternator. Procedural reading comprehension task poses new challenges. The main source of the challenge is due to the difference in nature of dynamic text versus static text. The entities are changing. There might be implicit mentions of entities or the attribute changes. For example, if you look at the sentence 2, there is no mention of mechanical energy or the fact that, or explicit mention that the fuel is getting destroyed. Also, the other challenge is due to the fact that we want to predict attribute values as spans of text instead of predefined classes, which gives the model more ability to generalize beyond what we can predefine for the problem. In this paper, we introduce new formalism for modeling procedural reading comprehension text. Each procedure is mapped to entities, attributes, and transitions. We also introduce DynaPro, a neural reading comprehension model that jointly predicts attributes and transitions. The attributes here are predicted either as spans of text or predefined classes. We also show that our model achieves the state of the art, and we provide a multiple analysis. Our model, DynaPro, leverages reading comprehension with inputting the entity aware context. The model predicts the attribute values either as predefined classes or spans of text. The model is trained end-to-end to optimize the prediction for predicting attribute and transition loss. And the output of the model are both attributes and transitions that are predicted over time. Let's start with how we can construct an input given process which contains a list of sentences, each individually describing an event, and the entity and the attribute that we want to track. We want to create an input for time step k and for entity 0. The first step is to ask a query about the entity and the location. If the location is the query about entity and attribute. If the attribute is location, we can ask where is the entity. Also, if we want to ask up to time point k, we truncated the process up to time point k, and we only include those sentences. We also include notations of predefined classes to have potential attribute classes as present as the span of text. After constructing this input, the input is passed through contextual embedding unit in order to get entity-aware representation. Here, the contextual embedding unit we used is the BERT embeddings. The entity-aware representation is then used for predicting attributes as predefined classes or spans of text. The predefined classes in our situations are a nowhere, somewhere, or span of text. With the attribute predictions, we move to create attribute-aware representation. The intuition is to rescale the original entity-aware representation based on the probability distribution of the attribute predictions for previous and current time step in order to capture the change. The entity-aware representation and attribute-aware representation then pass to the transition prediction module, which classifies over 4 different classes: destroy, move, create, and no transition. In order to have smoother predictions, we use a BiLSTM layer in order to have a memory of what are the previous predictions. As for the experiments, for our main benchmark, we use ProPara dataset. ProPara is a carefully annotated data containing around 400 scientific paragraphs for the training set. Over the ProPara, there are multiple test beds benchmarks introduced. The sentence level task asks about each prediction individually, if the transition is predicted, when and where it's predicted. The document level task also asks about the high level questions over the whole process. For example, it asks about the input, the output, or what are the conversions. The action dependency task asks if the transition that is predicted has further influence on the next predictions. As you can see in the chart, our model DynaPro achieves state-of-the-art over these benchmarks. We also did ablation study in order to measure the impact of the different components of our model. We observed that the joint predictions of transition and attributes is helpful by removing that this variation doesn't has lower performance than the original DynaPro. In order to measure the impact of attribute-aware representation, we did 2 experiments by removing the attribute-aware representation or replacing that with a classification token that is provided by BERT. And we see that both of these variation has lower performance than the DynaPro. We also showed the impact of truncating the input by feeding the full context and observing that the results are much lower. We also did qualitative analysis over our predictions, and we categorized our errors into 3 main categories. The first category of problems is due to incorrect class prediction. We observed that in most cases, our model tries to predict unknown location instead of predicting unknown. Our model is trying to push for a span. We also observed that there are incorrect span predictions. For example, in the example, we have to predict heart, whereas our model predicts right side of your heart. The third category of the problems are due to inconsistent transitions. We observe that as we build the tables incrementally, there are some transitions that are attempting to create entities that are already exist, moving entities that are destroyed, or destroying entities that are already destroyed. And these are the root of some inconsistency and errors. To summarize, we present a general formalism for modeling procedural reading comprehension task. We introduced DynaPro and neural model that is trained end-to-end to predict attributes and transitions. We also show that our model achieves state-of-the-art and over procedural reading comprehension task. Finally, thanks for listening to our talk.